So here's something to think about as you settle in tonight. Right now, at this very moment, somewhere in the world, a mathematician is staring at a piece of paper, or a whiteboard, or a glowing laptop screen in a dark office, everyone else long gone home, and they are stuck, completely, utterly stuck. Not stuck in the way you get stuck on a crossword clue, where you know the answer exists and you just can't quite reach it. Stuck in a deeper way, stuck on a problem that no human being has ever solved. A problem that the finest mathematical minds of the last century, or in some cases the last 2,000 years, have thrown themselves at and walked away from, humbled. And the wild thing, the thing that makes these problems so maddening and so beautiful at the same time, is that some of them are so simple to state that you could explain them to a 10-year-old. A child could understand the question, but the answer has defeated every single person who's ever tried. And that's what we're going to explore tonight. The great unsolved problems of mathematics. The questions that remain open, stubbornly, beautifully open, despite centuries of effort. We're going to take our time. There's absolutely no rush. We're going to start at the very beginning, with the oldest mathematical ideas humans ever had, and we're going to work our way forward through history, meeting the people who shaped these questions, the people who broke themselves trying to answer them, and the people who discovered that some questions might not have answers at all, which is itself a mind-bending idea we'll get to later. Some of these problems carry $1 million prize for their solution. Some of them touch the foundations of everything, from internet security to the weather forecast on your phone. And all of them, every single one, will show you something about the strange and beautiful nature of mathematics itself. This thing that humans invented, or discovered, depending on who you ask, and that turns out to be far deeper, far wilder, far more mysterious than most people ever realize. So get comfortable. Let your breathing slow down. If you drift off somewhere along the way, that's perfectly fine. Mathematics will still be here in the morning, still unsolved, still waiting. Let's start with the oldest question. What is mathematics, really? Because to understand why some problems remain unsolved, you need to understand what it even means to solve a mathematical problem, and that turns out to be a surprisingly deep question in its own right. Go back about 2,500 years, Greece. Specifically, the intellectual world of ancient Athens and the Greek colonies scattered across the Mediterranean and the coast of what is now Turkey. This is where something remarkable happened, something that, as far as we know, had never happened before in any civilization. People started demanding proof. Now, mathematics existed long before the Greeks. The Babylonians, working in Mesopotamia, in the Fertile Crescent between the Tigris and Euphrates rivers, had sophisticated mathematics going back to at least 2000 BCE. They wrote on clay tablets in cuneiform, and those tablets show that they could solve quadratic equations. They had tables of Pythagorean triples, sets of 3 numbers where the square of the largest equals the sum of the squares of the other two, like 3, 4, 5, or 5, 12, 13. And they had these 1,000 years before Pythagoras was born. The Egyptians had practical geometry for surveying their land after the Nile flooded every year, washing away the boundary markers between fields. Indian and Chinese mathematicians developed their own rich traditions. But in all of these cultures, mathematics was primarily practical. It was a tool. You used it to measure fields, predict eclipses, keep tax records, design temples. And the standard of truth was essentially, does it work? If a method gives you the right answer when you check it against reality, that's good enough. Move on. The Greeks changed that. They asked a different question. Not just does it work, but why does it work? Can you prove it? Can you show, through pure logical reasoning, starting from basic assumptions that everyone agrees on, that a mathematical statement must be true, Not just that it happens to be true in every case you've checked, but that it cannot possibly be false, ever, under any circumstances. That shift from calculation to proof is one of the most important intellectual moves in human history, and the person who crystallized it, who turned it into a systematic method, more than anyone else, was Euclid. Euclid of Alexandria. He lived around 300 BCE, and honestly, we know almost nothing about his personal life. Almost nothing. There are a few anecdotes, probably apocryphal. One story says that when King Ptolemy asked him if there was a shorter way to learn geometry than working through all of his books, Euclid replied that there is no royal road to geometry. Great line, whether he actually said it or not. Another story has a student ask Euclid what practical benefit he would gain from studying geometry, at which point Euclid supposedly turned to his servant and said, "Give this man a coin, since he must make a profit from everything he learns." But what we do have, what survived intact for over 2,000 years and became possibly the most influential textbook ever written, is his Elements. The Elements is not just a geometry book, though it contains a tremendous amount of geometry. It's a demonstration of a method. Euclid starts with a small number of definitions, postulates, and common notions. Things he asks you to accept without proof, because they're so basic and self-evident that trying to prove them would be circular. Things like, a straight line can be drawn from any point to any other point, or all right angles are equal to each other. Simple, almost obvious statements. And then, from those handful of starting points, he builds, theorem by theorem, proposition by proposition, an enormous edifice of mathematical truth. Each theorem is proved rigorously from the ones before it, which were proved from the ones before those, all the way back to the original postulates. It's like a cathedral built from pure logic, and it stood, essentially unchallenged, for over 2 millennia. Abraham Lincoln studied it as a young lawyer, teaching himself logical reasoning by working through the propositions. Einstein encountered it as a boy and later described the experience as awakening a sense of wonder that never left him. Bertrand Russell called it one of the greatest achievements of the human intellect. The Elements has been in continuous use longer than any other textbook in any subject, in any civilization, ever. And here's the thing that matters most for our story tonight. One of the topics Euclid explored in his Elements was prime numbers. And prime numbers, it turns out, are where some of the deepest, most stubborn, most beautiful unsolved problems in all of mathematics live. So let's talk about primes. A prime number is a number greater than 1 that can only be divided evenly by 1 and itself. 2 is prime. It's only divisible by 1 and 2. 3 is prime. 4 is not, because it's 2 times 2. 5 is prime. 6 is not. It's 2 times 3. 7 is prime. And so on. The first few primes are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. You can feel the pattern, or rather, you can feel the almost pattern. They're not evenly spaced. They thin out as you go higher, but irregularly, unpredictably. Sometimes 2 primes huddle close together, like 11 and 13, or 17 and 19. Sometimes there are big gaps. There's no simple formula that generates all the primes and nothing but the primes. They seem to have a mind of their own. Now, why should anyone care so much about prime numbers? Here's the thing. Primes are the atoms of arithmetic. Every whole number greater than 1 is either prime itself or can be broken down into a product of primes in exactly one way. 12 is 2 times 2 times 3. 30 is 2 times 3 times 5. 100 is 2 times 2 times 5 times 5. This is called the fundamental theorem of arithmetic, and Euclid essentially proved it. though it was stated more precisely by later mathematicians. It means that the prime numbers are the building blocks from which all other whole numbers are constructed, the way elements in chemistry are the building blocks of all molecules. If you understand the primes, you understand the deep structure of the integers. If you don't, there's a whole layer of mathematical reality that remains hidden from you. And the first big question about primes is the simplest one imaginable. How many are there? Do they go on forever, or do they eventually stop? Is there a largest prime, somewhere out there, some unfathomably enormous number, after which every number can be broken into smaller factors? Euclid answered this question, and his proof that there are infinitely many primes is one of the most beautiful arguments in all of mathematics. It's so elegant, so clean, that it's worth walking through, even if you've never thought about mathematical proofs before. Here's how it goes. Suppose, just for the sake of argument, that there are only finitely many primes. Suppose you could write them all down in a list, P1, P2, P3, all the way up to Pn, the very last prime. Now, do something clever. Multiply all of them together and add 1. Call this new number Q. So Q equals P1 times P2 times P3 times all the rest times Pn plus 1. Now Q is some definite number. It's either prime or it isn't. If Q is prime, well, we've just found a new prime that wasn't in our list, because Q is bigger than every number on the list. That's a contradiction. But what if Q isn't prime? Then it must be divisible by some prime. But here's the clever part. It can't be divisible by any prime on our list, because when you divide Q by any of the primes P1 through Pn, you always get a remainder of 1. That's exactly how Q was constructed. It's the product of all of them, plus 1. So whatever prime divides Q, it must be a prime that's not in our list. Either way, our assumption that we had a complete list of all the primes leads to a contradiction. Therefore, there is no such complete list. The primes go on forever. That's it. That's the whole proof. It's been called the most elegant argument in mathematics, and it's over 2,300 years old, and it answers our first question beautifully. Primes never run out. But it immediately opens up deeper questions, harder questions. Yes, there are infinitely many primes, but how are they distributed among the integers? Is there a pattern to how they're sprinkled along the number line? Can we predict, even approximately, how many primes there are below a given number? And are there patterns within the primes, pairs, clusters, regularities, that persist forever, no matter how far out you go? These questions sound simple. Some of them have haunted mathematicians for centuries, and several of them remain completely unsolved tonight. Let's start with one of the oldest and most famous. When you look at the list of small primes, you notice that sometimes primes come in pairs that are only 2 apart. 3 and 5, 5 and 7, 11 and 13, 17 and 19, 29 and 31, 41 and 43. These are called twin primes. 2 primes side by side with nothing but a single even number between them. And the question, the devastating, beautiful, simple question, is, do twin primes go on forever? Think about that for a second. We know there are infinitely many primes. Euclid proved that. But among those infinitely many primes, do pairs that are just 2 apart keep showing up forever? Or do they eventually stop? Does there come a point, way out in the number line, past numbers so large that they would take more digits to write down than there are atoms in the observable universe, where you would never again find 2 primes separated by just 2? Nobody knows. As of right now, tonight, this is unsolved. The twin prime conjecture, the belief that twin primes go on forever, has been held by most mathematicians for well over a century. Computers have found enormous twin primes, pairs with hundreds of thousands of digits, but no one has been able to prove that they never stop. And here's what's so maddening about it. The statement is so simple. You could explain it to anyone. Two primes, close together, forever or not? That's the whole question. A child could understand it. But the proof, if it exists, seems to require understanding the distribution of prime numbers at a level of precision and depth that current mathematics simply hasn't reached. Now, there has been spectacular progress, and the story behind that progress is one of the most remarkable human stories in recent mathematics. In 2013, a mathematician named Yitang Zhang, working at the University of New Hampshire, proved something that electrified the mathematical world. He proved that there are infinitely many pairs of primes that differ by at most 70 million. Now, 70 million is a lot bigger than 2. But think about what Zhang actually showed. Before his paper, mathematicians couldn't prove that there was any finite gap, any fixed, bounded distance that contained infinitely many prime pairs. For all anyone could prove, the gaps between consecutive primes might grow without bound, stretching to infinity, with pairs of close primes becoming rarer and rarer until they vanish entirely. Zhang proved that no, there is some fixed bound, at most 70 million, such that you will always, no matter how far out you go on the number line, find another pair of primes within that gap. The primes might thin out, but they never stop clustering, and Zhang's personal story makes it even more compelling. He wasn't a star professor at MIT or Princeton. He'd had a genuinely difficult career. He earned his PhD from Purdue University in the early 1990s, but his relationship with his doctoral advisor had been strained. Some accounts suggest the advisor made it difficult for Zhang to get recommendation letters. For years after his PhD, Zhang couldn't find an academic position. He worked various jobs. He was a delivery driver. He worked at a Subway sandwich restaurant. He did accounting for a friend's business. He lived frugally, moving from place to place, but he never stopped doing mathematics. He kept working, quietly, stubbornly, on problems that interested him, without institutional support, without colleagues to bounce ideas off of, without anyone really paying attention. He would go for long walks, turning ideas over in his head, letting problems simmer. Later, he described a key moment of insight as happening during a visit to a friend's backyard in Colorado. He was watching deer, not even thinking about mathematics directly, when something clicked. And then, in his late 50s, he submitted a paper to the Annals of Mathematics, one of the most prestigious journals in the field, and the paper was sent out for review, and the reviewers came back and said, "The proof is correct. The result is real." Yitang Zhang, a part-time lecturer at the University of New Hampshire, a man who had been essentially invisible to the mathematical establishment for 20 years, had just proved one of the biggest results in analytic number theory in decades. The mathematical community responded with extraordinary energy. A collaborative online project called Polymath 8 formed almost immediately, bringing together mathematicians from around the world to push Zhang's bound down from 70 million. Within months, using refinements of Zhang's methods and new ideas, they got it down to about 4,000. Then James Maynard, a young British mathematician, he was in his 20s at the time, which is remarkable given the difficulty of the problem, independently developed new techniques that brought the bound down further. As of the last confirmed results, the best-known bound is 246, meaning we know there are infinitely many pairs of primes that are at most 246 apart, but getting from 246 down to 2, proving the actual twin prime conjecture, seems to require fundamentally new ideas. The methods that got us this far, as powerful and ingenious as they are, appear to have hit a wall. Getting to 2 might need an entirely different approach, something nobody has thought of yet. And that's where it stands tonight. 246. Tantalizingly close in spirit, but an ocean away in mathematics. Twin primes are just one piece of a much larger puzzle about prime numbers. There's another ancient question, even older in its origins, that's just as simple and just as stubbornly unsolved. It's called the Collatz Conjecture, and it goes like this. Every even number greater than 2 can be written as the sum of 2 primes. 4 equals 2 plus 2. 6 equals 3 plus 3. 8 equals 3 plus 5. 10 equals 5 plus 5, or you could also write it as 3 plus 7. 12 equals 5 plus 7. 14 equals 3 plus 11, or 7 plus 7. You can keep going as long as you like. Every even number anyone has ever checked can be written this way. Computers have verified it for even numbers up to 4 times 10 to the 18th power. That's 4 followed by 18 zeros, and beyond. Every single one works. No counterexample has ever been found, but no one has proved it. Nobody has been able to show that it must always work, that somewhere out in the unimaginably vast reaches of the number line, there isn't an even number that simply refuses to be written as the sum of 2 primes. It's another one of those problems where the question fits on a napkin, and the answer seems to require the entire ocean. The conjecture takes its name from Christian Goldbach, a Prussian mathematician who mentioned it in a letter to Leonhard Euler in 1742. And Euler, well, we need to talk about Euler, because he's one of the most important figures in this entire story, and we're going to keep running into him all night. Leonhard Euler was born in Basel, Switzerland, in 1707, and he was, by any reasonable measure, the most prolific mathematician who has ever lived. The sheer volume of his output is almost incomprehensible. He published over 800 papers in his lifetime, papers on number theory, calculus, mechanics, optics, astronomy, graph theory, music theory, naval architecture. After his death, the Journal of the St. Petersburg Academy was still publishing his backlog of papers for decades. A project to collect and publish his complete works, called the Opera Omnia, was started in 1911, and it's still not finished. The man wrote mathematics the way other people breathe. Euler's story takes him across the great courts and academies of 18th century Europe. He spent much of his early career in St. Petersburg, at the invitation of the Russian Academy of Sciences. This was Peter the Great's Russia, rapidly trying to modernize, importing European scholars to build a world-class scientific establishment. Euler thrived there, but the political turmoil that followed Peter's death made life difficult, and eventually Euler accepted an invitation from Frederick the Great of Prussia to join the Berlin Academy. Frederick was brilliant, witty, cultured, and somewhat dismissive of Euler. Frederick wanted a salon philosopher, someone charming and eloquent who could dazzle the court with sophisticated conversation. Euler was none of those things. He was plain-spoken, practical, deeply religious, and entirely focused on his work. Frederick once called him a mathematical cyclops, partly because of the eye he'd lost, and partly because he considered Euler socially one-dimensional. The relationship was always strained. After 25 years in Berlin, during which he produced an astonishing body of work, Euler returned to St. Petersburg, where he spent the rest of his life. And here's the part of Euler's story that always gets me. He started losing the sight in his right eye in his late 20s, probably due to an infection or a strain from staring at the sun during astronomical observations. The exact cause is debated. By his mid-30s, that eye was essentially useless. And then, in 1766, at the age of 59, He lost the sight in his remaining eye after a botched cataract operation. He went completely blind. You might think that would be the end of a mathematical career. It wasn't even a speed bump. Euler reportedly said that losing his sight removed distractions, and his mathematical output actually increased after going blind. He could perform enormous calculations entirely in his head and dictate the results to his sons and assistants, who would write out the papers. In the years after his blindness, he produced nearly half of his total life's work. He once settled an argument between two students who disagreed about the 50th decimal place of a complicated series by computing the entire thing in his head. The man was, to put it plainly, extraordinary. Euler's death in 1783 was characteristically undramatic. He spent the afternoon calculating the orbit of the recently discovered planet Uranus and playing with his grandchildren. He suffered a brain hemorrhage in the early evening, and, in the words of the mathematician, the Marquis de Condorcet, he ceased to calculate and to live. He was 76. Euler thought the Goldbach conjecture was probably true, but couldn't prove it. That was in 1742. 280-some years later, neither can anyone else. And the pattern repeats across mathematics. Questions about primes that are almost trivially easy to ask and seemingly impossible to answer. But here's why all of these prime number questions ultimately point in one direction. To truly understand the distribution of primes, to answer twin primes or Goldbach or any of the other deep conjectures about how primes are scattered among the integers, you would need to understand a single mathematical object more deeply than anyone currently does. An object that sits at the heart of analytic number theory, that connects prime numbers to the most powerful tools of analysis and geometry, and that gives rise to what many mathematicians consider the single most important unsolved problem in all of mathematics, a problem that carries a $1 million prize from the Clay Mathematics Institute, a problem that has consumed the lives of some of the greatest mathematicians of the last 160 years, the Riemann Hypothesis. To understand the Riemann Hypothesis, we need to talk about a man named Bernhard Riemann and a particular mathematical function called the zeta function. And to get there, we should start with Euler again, because he's the one who first studied this function, decades before Riemann transformed it into something nobody expected. One of the many things Euler investigated was the sum of the reciprocals of the natural numbers raised to a power. That sounds more technical than it really is. Here's what it means. Pick a number, call it s. Now calculate 1 over 1 to the power s, plus 1 over 2 to the power s, plus 1 over 3 to the power s, plus 1 over 4 to the power s, and keep going, adding terms forever. When s equals 2, for instance, you're adding up 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25, the reciprocals of the perfect squares. Euler figured out that this particular sum converges to exactly pi squared divided by 6. And that's remarkable. Think about what just happened. You took a sum involving nothing but whole numbers and their squares, the most discrete, arithmetic, number-theoretic objects you can imagine. And the answer involves pi, the ratio of a circle's circumference to its diameter. The circle, which lives in geometry, sneaks into the integers. That kind of unexpected connection between different branches of mathematics is everywhere in the subject, and it's one of the things that makes mathematicians fall in love with it. There's a hidden unity to mathematics, a sense that all the different fields are secretly aspects of one underlying structure. And when you find a connection like this, you catch a glimpse of that unity. This infinite sum, considered as a function of the variable s, is what we now call the Riemann zeta function, though Euler studied it long before Riemann was born. Euler proved a stunning connection between this sum and the prime numbers. a formula showing that the zeta function can be expressed as a product over all prime numbers, linking this analytical object to the atoms of arithmetic. It was one of the first hints that analysis, the world of continuous functions and infinite series, has a deep and mysterious relationship to number theory, the world of whole numbers and primes. But it was Riemann who took this function and turned it into something transcendent. Bernhard Riemann was born in 1826 in the tiny village of Bresselenz in the Kingdom of Hanover, in what is now northern Germany. His father was a Lutheran pastor in a poor rural parish. The family had very little money. Riemann was shy, anxious, physically frail, and plagued by poor health throughout his short life. As a child, he was painfully timid. He struggled with social situations and was terrified of speaking in front of others. His father initially wanted him to study theology and follow in his footsteps, and Riemann tried, enrolling at the University of Göttingen to study theology. But mathematics kept pulling at him. He attended lectures by Carl Friedrich Gauss, the greatest mathematician alive at the time, and the pull became irresistible. His father gave his blessing, and Riemann devoted himself entirely to mathematics. He suffered from what was probably tuberculosis, though it wasn't formally diagnosed until later. He was socially awkward, terrified of public speaking, which is ironic, because his habilitation lecture on the foundations of geometry, delivered in 1854 before a small audience at the University of Göttingen, is one of the most important mathematical presentations ever given. Gauss, who was in the audience, was reportedly deeply impressed. This from a man who was famously stingy with praise. In that single lecture, Riemann outlined a new conception of geometry that would, decades later, provide Einstein with exactly the mathematical framework he needed to formulate general relativity. Riemann essentially created the geometry of curved spaces 50 years before anyone needed it for physics. He imagined spaces where the rules of Euclidean geometry don't apply, where parallel lines can meet, where the angles of a triangle don't add up to 180 degrees, where space itself curves and bends. It was pure mathematics at its most visionary, decades ahead of its time. But Riemann was also one of those rare thinkers who didn't just solve problems. He saw entirely new landscapes that nobody else had perceived. He didn't write many papers. His total output was small compared to someone like Euler, but nearly every paper he wrote reshaped whatever field it touched. His doctoral thesis, supervised by Gauss, revolutionized complex analysis. His work on the foundations of geometry became essential to general relativity. And then there's the paper that concerns us tonight. In 1859, upon his election to the Berlin Academy of Sciences, Riemann submitted a paper, just one paper, 8 pages long. Its title translates from German as On the Number of Primes Less Than a Given Magnitude, 8 pages. And those 8 pages are arguably the most consequential 8 pages in the history of number theory, and perhaps in all of mathematics. Here's what Riemann did. He took Euler's zeta function, that infinite sum involving reciprocals of powers, and he extended it, using a brilliant technique called analytic continuation, to the entire complex plane. Now, the complex plane is where you allow the variable s to be not just an ordinary real number, but a complex number, a number with both a real part and an imaginary part, involving the square root of -1. If you haven't encountered complex numbers before, don't worry about the technical details. Just think of them as points on a 2-dimensional plane instead of a 1-dimensional number line. The horizontal direction represents the ordinary real numbers you're used to. The vertical direction represents the imaginary part. Every point on this plane corresponds to a complex number, and Riemann showed that the zeta function could be meaningfully defined, extended in a natural, unique way, to almost every point on this plane, not just the real numbers greater than 1, where Euler's original sum converges. And then Riemann asked a simple question. Where does this extended function equal 0? Where are the zeros of the zeta function? Some zeros are easy to find. They occur at the negative even integers, -2, -4, -6, and so on. These are called the trivial zeros, because they're well understood and, mathematically speaking, not very interesting. But there are other zeros, infinitely many of them, hiding in a particular vertical strip of the complex plane, the strip where the real part of S is between 0 and 1. These are the non-trivial zeros, and they are the heart of everything. Riemann calculated a few of these non-trivial zeros and noticed something extraordinary. They all seemed to lie on a single vertical line, the line where the real part of S equals exactly 1/2, right down the middle of the critical strip. And almost in passing, as a remark that takes up barely a sentence in his 8-page paper, he noted that it was very likely that all the non-trivial zeros lie on this line. That's it. That offhand comment is the Riemann hypothesis. All non-trivial zeros of the Riemann zeta function have real part equal to 1/2. Now, you might reasonably ask, why should anyone care where the zeros of some function in the complex plane happen to fall? And the answer is the deepest magic in Riemann's paper. He showed that the distribution of prime numbers, exactly how they're sprinkled among the integers, how many primes there are below any given number, how they thin out as numbers get larger, is controlled with exquisite precision by the locations of these zeros. The primes and the zeros of the zeta function are locked together in a kind of mathematical dance, each one constraining and shaping the other. If the Riemann hypothesis is true, if all those non-trivial zeros really do line up on that critical line with real part 1/2, then the prime numbers are distributed as regularly as they possibly can be. Our best approximations for counting primes would have the smallest possible error. The primes would wander, yes, but they'd wander within a narrow, well-understood band. The hidden music of the primes would be playing in a known key. And if the Riemann hypothesis is false, if even a single zero lies off that critical line, then the primes contain surprises that our current understanding completely misses. There would be unexpected fluctuations in their distribution, regions where primes cluster more densely or more sparsely than our best formulas predict. The orderly picture would crack. Since 1859, mathematicians have computed trillions of non-trivial zeros of the zeta function. Every single one of them lies on the critical line. Not one exception has ever been found. The computational evidence is overwhelming, almost absurdly strong. But evidence is not proof, and in mathematics, only proof counts. The Riemann hypothesis remains unproven. The list of great mathematicians who have tried and failed to prove it reads like a hall of fame. G.H. Hardy proved in 1914 that infinitely many zeros lie on the critical line, but couldn't show that all of them do. David Hilbert, the towering figure of early 20th century mathematics, reportedly said that if he fell asleep and woke up after 500 years, the first thing he'd ask is whether the Riemann hypothesis had been proved. The great Atlas Selberg won a Fields Medal, partly for work related to the zeta function. André Weil proved an analog of the Riemann hypothesis for related functions, also earning a Fields Medal. But the original hypothesis, for the original Riemann zeta function, stands open. It's been open for over 160 years, and it shows no clear signs of yielding. And then there's a remarkable twist in the story that connects the Riemann hypothesis to physics, specifically to the world of quantum mechanics. In 1972, a young mathematician named Hugh Montgomery was visiting the Institute for Advanced Study in Princeton. He had been studying the statistical spacing between zeros of the zeta function, not just where they are, but how they're spaced relative to one another. Over tea, he happened to mention his results to the physicist Freeman Dyson. Montgomery described the formula he'd derived for the pair correlation of the zeros. Dyson looked at it and immediately recognized it. It was the same formula that describes the spacing between energy levels of heavy atomic nuclei in quantum mechanics, a result from an entirely different field called random matrix theory. Think about what that means. The zeros of the Riemann zeta function, which control the distribution of prime numbers, appear to be statistically distributed in exactly the same way as the energy levels of quantum systems. Number theory and quantum physics, two subjects that seem to have nothing whatsoever to do with each other, were speaking the same mathematical language. Physicists talk about the music of the primes, and they're not just being poetic. There really does seem to be a hidden structure, some deep connection between the quantum world and the world of prime numbers that nobody fully understands. Some mathematicians believe that proving the Riemann hypothesis may ultimately require ideas from physics, that the zeros of the zeta function might literally be the energy levels of some undiscovered quantum system, and that the Riemann hypothesis would follow from the physical requirement that energy levels must be real numbers. It's a tantalizing idea, and it hasn't been made rigorous, but it hints at a unity between mathematics and physics that goes even deeper than anyone had imagined. Riemann himself never got to explore his hypothesis deeply. He died in 1866, at the age of just 39, of tuberculosis, while traveling in Italy with his wife, trying to recover his health in the warm air near Lake Maggiore. He died on a Friday afternoon in Salaska. His housekeeper, not understanding the significance of his unpublished manuscripts, reportedly burned many of them after his death. We'll never know what was in those pages. What survived, those 8 pages from 1859, plus his other published works, changed mathematics forever. And that casual remark about the zeros, that almost throwaway conjecture, became the most famous unsolved problem in the history of the subject. And it matters far beyond pure mathematics. Modern cryptography, the security that protects your online banking, your passwords, your encrypted messages, every secure transaction on the internet, is built on assumptions about the difficulty of factoring large numbers into their prime components. The distribution of primes is not an abstract curiosity. It's a practical foundation of digital security. The Riemann hypothesis wouldn't directly break existing cryptographic systems, but it would sharpen our understanding of prime numbers in ways that could have profound implications for how we think about the mathematical bedrock on which that security rests. Now, I want to shift gears, because the story of unsolved mathematics doesn't stay in the ancient world of numbers. In the 20th century, mathematicians discovered something astonishing and, honestly, unsettling about the very foundations of their subject. They discovered fundamental, inescapable limits on what mathematics can do, what can be proved, what can be computed. And those discoveries opened up questions that make even the Riemann hypothesis seem almost classical in comparison. The story starts in the early 1900s, at a moment when mathematics was brimming with confidence. The central figure in this part of the narrative is David Hilbert, a German mathematician based at the University of Göttingen, the same university where Riemann and Gauss had worked. And by the turn of the 20th century, Hilbert was arguably the most influential mathematician alive. He had a grand vision. He believed that all of mathematics could be built on a solid, consistent, complete logical foundation. You could, in principle, write down a set of axioms, a set of basic rules, from which every true mathematical statement could be derived through mechanical logical deduction, and no contradictions would ever arise. Mathematics would be a perfect system. Every question would have an answer. Nothing would be left uncertain. In 1900, at the International Congress of Mathematicians in Paris, Hilbert delivered a legendary address in which he presented a list of 23 problems that he considered the most important unsolved challenges for the coming century. It was an extraordinary act of intellectual leadership. One mathematician standing up and setting the agenda for an entire discipline. We must know. We will know, Hilbert declared. That confidence, that belief in the unlimited power of human reason to resolve every mathematical question, defined an era. Many of those problems were eventually solved over the following decades, some leading to Fields medals and Nobel Prizes. But Hilbert's broader dream, the dream of a complete, consistent, self-guaranteeing foundation for all of mathematics, was about to collide with reality. In 1931, a quiet, meticulous, 25-year-old Austrian logician named Kurt Gödel published a paper that shattered Hilbert's program. It's sometimes described as the most important result in mathematical logic since Aristotle. Gödel proved two theorems, his incompleteness theorems, and their implications are still reverberating through mathematics, philosophy, and computer science today. The first incompleteness theorem says this: in any consistent formal system that's powerful enough to express basic arithmetic, and by consistent, we mean it never contradicts itself, there exist true statements that cannot be proved within that system. Let that sink in for a moment. It's not saying that we're not smart enough to find the proofs. It's saying the proofs don't exist. Within the rules of the system, there are mathematical truths that are permanently, inherently beyond reach, not temporarily, not due to lack of effort, permanently. The system is incomplete, and not because it's badly designed. You could try to fix it by adding more axioms, but Gödel showed that any expanded system, as long as it's consistent and powerful enough to talk about numbers, will have its own unprovable truths. Incompleteness is inescapable. The second incompleteness theorem twists the knife. It says that such a system cannot prove its own consistency. You cannot use the rules of arithmetic to prove that arithmetic will never produce a contradiction. You'd need a more powerful system to do that, and then you'd need an even more powerful system to prove the consistency of that one, and so on forever. There's no final bedrock, no ultimate foundation. Hilbert's dream of a self-certifying mathematical system is logically impossible. Gödel himself was a fascinating and deeply troubled figure. After his groundbreaking work, he emigrated to the United States in 1940, fleeing the rise of Nazism, and spent the rest of his career at the Institute for Advanced Study in Princeton. There, he formed an unlikely and touching friendship with Albert Einstein. The two men, both exiles, both geniuses, would walk together every day along the tree-lined paths of the Institute, deep in conversation. Einstein once confided to a colleague that in his later years, his own work didn't amount to much, and that he went to the Institute mainly for the privilege of walking home with Gödel. They were an odd pair. Einstein, gregarious and rumpled, and Gödel, precise and reclusive, bundled in a heavy overcoat, even in warm weather, because he was perpetually cold. As Gödel aged, his personality grew increasingly eccentric. He developed intense paranoia, particularly about his food being poisoned. He would eat only food that his wife, Adele, prepared for him. When Adele was hospitalized in 1977, unable to cook for him, Gödel simply stopped eating. He died in January 1978, weighing barely 30 kilograms. The death certificate listed the cause as malnutrition and inanition due to personality disturbance. The man who proved the limits of formal systems was, in the end, consumed by the limits of his own mind. It's one of the saddest stories in the history of science. Gödel's theorems didn't destroy mathematics. Mathematics kept going, kept producing beautiful and useful results. But they changed its philosophy in a fundamental way. They showed that the mathematical universe is inexhaustible, that no finite set of axioms can capture all mathematical truth. There will always be more. There will always be statements that are true but unprovable. And that raises a haunting possibility about unsolved problems. Some of them might be unsolvable, not because we're not clever enough, but because they're independent of our axioms. They could be true, or they could be false. And no amount of logical reasoning from our starting assumptions will ever settle the matter. We'll come back to this idea later, when we talk about the continuum hypothesis. But right now, Gödel's work is a bridge to the next great unsolved problem, because it fed directly into the thinking of another extraordinary mind, a man who asked a related but different question, and, in answering it, invented the conceptual foundation of every computer that has ever existed. Alan Turing, born in London in 1912, a solitary, brilliant, somewhat eccentric young man who loved long-distance running. He was nearly Olympic caliber, with a marathon time of 2 hours and 46 minutes, and had a habit of chaining his coffee mug to the radiator to prevent it from being stolen. As a schoolboy, he had formed a close friendship with a slightly older boy named Christopher Morcom, a talented student who shared Turing's passion for science. When Morcom died suddenly of bovine tuberculosis at 17, the loss devastated Turing and may have shaped his later interest in the relationship between mind and mechanism, whether the essence of a person could, in some sense, survive in a machine. At the age of 23, Turing published a paper that defined, once and for all, what computation means. The question he was addressing had been posed by Hilbert. Is there a definite mechanical procedure, an algorithm, that can determine whether any given mathematical statement is provable? Hilbert called this the Entscheidungsproblem, German for decision problem, and to answer it, Turing first had to define precisely what a mechanical procedure actually is. His answer was an imaginary machine, what we now call a Turing machine. It's almost comically simple in concept. An infinitely long tape divided into cells, each cell holding a symbol. A head that reads the current symbol, writes a new symbol, and moves one cell left or right, all according to a finite table of rules. That's the whole thing. And Turing proved that this absurdly simple device can compute anything that is computable. Any algorithm, any calculation, any logical procedure that can be carried out step by step, a Turing machine can do it. If a Turing machine can't do it, nothing can. No future computer, no matter how powerful, will be able to do it either. And then Turing proved that no Turing machine can solve the Entscheidungsproblem. There's no algorithm that can take an arbitrary mathematical statement and determine, in a finite number of steps, whether it's provable. Some questions are algorithmically undecidable. The limits that Gödel found in the world of proof, Turing found in the world of computation. During World War II, Turing put these ideas to devastating practical use at Bletchley Park, the British code-breaking center, where he played a central role in breaking the German Enigma cipher. His work there, designing electromechanical machines called bombays that could test thousands of possible Enigma settings, is estimated to have shortened the war by at least 2 years and saved millions of lives. After the war, he was one of the first people to design a general-purpose electronic computer. He also wrote a pioneering paper on artificial intelligence, proposing what we now call the Turing test, as a way to determine whether a machine can think. But Turing's story ends in tragedy. In 1952, he was prosecuted for homosexuality, which was illegal in Britain at the time. He was convicted and given a choice between imprisonment and chemical castration through hormone injections. He chose the injections. 2 years later, on June 7, 1954, he was found dead in his bedroom, with a half-eaten apple beside him. The cause of death was cyanide poisoning. He was 41 years old. It took until 2013 for the British government to grant him a posthumous royal pardon. The man who had arguably done more than any other individual to win the war and invent the modern computer had been destroyed by the very society he helped save. Now all of this, Gödel, Turing, the limits of logic and computation, might sound hopelessly abstract. It's not, because these foundational ideas lead us, through a chain of reasoning that took several decades to develop, to what is widely considered the most important unsolved problem in theoretical computer science. A problem that, if solved either way, would have immediate, massive, real-world consequences. A problem that is so important, it was designated one of the 7 Millennium Prize problems by the Clay Mathematics Institute, each carrying that $1 million prize. It's called P versus NP. Here's the setup, and I'll take it slowly, because this is one of those ideas that seems abstract at first, but is actually about something you experience every day. Think about problems that computers solve. Some problems are easy, in the sense that there exist fast algorithms, efficient step-by-step procedures, that can solve them even when the input is enormous. Sorting a list of 1 million names into alphabetical order, a modern computer can do that in a fraction of a second, using clever algorithms like merge sort or quicksort, finding the shortest path between 2 cities in a road network with millions of intersections. There are efficient algorithms for that too. These kinds of problems, where the time required grows in a manageable way, what mathematicians call polynomial time, as the size of the input increases, belong to a class called P. The P stands for polynomial time. But there's another class of problems where finding a solution seems to be incredibly hard, but checking whether a proposed solution is correct is easy. Here's a concrete example. Suppose I give you a large number, a number with, say, 600 digits, and I ask you to find its prime factors, to break it down into the prime numbers that multiply together to give it. That's brutally hard. The best algorithms we have would take longer than the age of the universe to factor a 600-digit number on the fastest conventional computer on Earth. But now suppose I just hand you a proposed factorization. Here, I claim these specific primes are the factors. Checking it is trivial. You just multiply them together and see if you get the original number. A computer can do that in milliseconds. Finding is hard. Checking is easy. Here's another example that's maybe more intuitive. Think about a jigsaw puzzle with 1,000 pieces. Assembling it, finding where each piece goes, could take you hours or days. But if someone hands you a completed puzzle, checking that it's correct takes a glance. Or, think about the traveling salesman problem, one of the most famous problems in computer science. A salesman needs to visit 100 cities, each exactly once, and return to the starting city, traveling the shortest possible total distance. Finding the optimal route is incredibly hard. The number of possible orderings of 100 cities is larger than the number of atoms in the observable universe. But if someone gives you a specific route and claims it's shorter than, say, 10,000 miles, checking that claim is simple. You just add up the distances along the route. Problems where a proposed solution can be verified quickly belong to a class called NP, and the billion-dollar question, maybe literally, given its implications, is this: does P equal NP? Are these two classes the same? Is every problem whose solution can be quickly checked also a problem whose solution can be quickly found? If P equals NP, the consequences would be staggering. Finding a mathematical proof would be no harder than checking one. Cracking a code would be as easy as creating one. Designing the ideal protein shape to cure a disease would be as easy as testing whether a given protein works. Optimizing any complex system, a supply chain, an airline schedule, a power grid, would become as easy as verifying that the optimization was correct. The entire distinction between creation and verification would collapse. Most computer scientists and mathematicians believe this isn't the case. They believe P does not equal NP, that there are genuinely, inherently hard problems where finding a solution is unavoidably, fundamentally harder than checking one. The world certainly behaves as if this is true. Our entire digital security infrastructure, passwords, encryption, secure communications, online banking, all of it rests on the assumption that certain problems are hard to solve, even though solutions are easy to check. If P equaled NP, most of modern cryptography would crumble overnight. Your bank account password, your encrypted emails, your secure web connections, all of it would become trivially breakable, but nobody has proved it. Despite half a century of effort by thousands of researchers, nobody has proved that P and NP are different classes, and nobody has proved they're the same. The problem remains wide open, and what makes it especially frustrating is that people have actually proved that certain specific proof techniques, certain broad strategies, are incapable of resolving the question. It's as if the problem is protected by walls, and every time someone identifies a possible way in, mathematicians discover that approach has a fundamental limitation that prevents it from reaching the goal. Rasbarov and Rudik showed that one major class of techniques, called natural proofs, can't work. Baker, Gill, and Solovey showed that another approach, called relativization, can't work either. The problem seems to demand entirely new mathematical ideas that nobody has had yet. So we've traveled from the ancient world of primes into the modern world of computation, and we've met three of the most famous unsolved problems: the Riemann hypothesis, the twin prime conjecture, and P versus NP. Now let's take a turn into the physical world, because some of the deepest unsolved problems in mathematics aren't about abstract numbers or logical systems. They're about the real, physical world, about water and air, and the forces that hold atoms together. And the surprising thing is this: we do not have a complete mathematical understanding of how fluids behave. Not water, not air, not anything that flows. Leonardo da Vinci was obsessed with this. In the late 15th century, he sat by rivers and watched the water churn, sketching the patterns of turbulence with an artist's eye and a scientist's curiosity. His drawings of water flowing past obstacles, the swirling vortices, the curling eddies, are hauntingly beautiful and scientifically prescient. He could see the complexity of fluid motion, and he knew it was trying to tell him something, but the mathematical language to describe it wouldn't exist for another 300 years. The equations that describe fluid motion have been known since the 1820s and 1840s. They're called the Navier-Stokes equations, named after Claude Louis Navier, a French engineer and physicist, and George Gabriel Stokes, an Irish-born mathematician and physicist. Navier was an engineer at heart. He helped design bridges and was interested in practical problems of water flow and structural mechanics. Stokes was more of a pure mathematician, meticulously rigorous. Between them, working independently and from slightly different starting points, they derived the equations that bear their names. These equations are based on Newton's second law, force equals mass times acceleration, applied not to a single object, but to a continuous fluid. They account for pressure, viscosity, and external forces, and they describe how the velocity of a fluid at every point in space changes over time. For nearly 2 centuries, They've been the foundation of fluid dynamics. Every airplane wing, every weather model, every simulation of blood flowing through an artery, every animated ocean wave in a movie, every calculation an engineer makes about how air moves over a car body or how water flows through a pipe. Underneath all of it, somewhere, the Navier-Stokes equations are at work. But here's the unsolved problem. When you start with some smooth, well-behaved initial state, some description of how the fluid is moving at time zero, and you try to evolve the equations forward in time, we don't know whether the solution will always remain smooth and well-behaved, or whether it might develop what mathematicians call a singularity. A singularity is a point where some quantity, like the velocity of the fluid, or the rate at which velocity is changing, goes to infinity, blows up, becomes mathematically meaningless, and if a singularity forms, the equations break down, because no real fluid can have infinite velocity. Physics stops. The Millennium Prize problem asks this precisely. For the three-dimensional Navier-Stokes equations, starting from smooth initial conditions with reasonable behavior at infinity, do solutions always exist for all future times? And do they stay smooth? Or can singularities form in finite time? For two-dimensional fluids, think of a thin layer of oil spreading on water, essentially flat. The answer is known. Smooth solutions always exist. That was proved in the 1960s by the Russian mathematician Olga Ladizhenskaya, a remarkable figure who overcame extraordinary obstacles. Her father, a mathematics teacher, was arrested during Stalin's purges in 1937 and executed. As the daughter of a so-called enemy of the people, she was branded by association. She was denied admission to Leningrad State University. She was barred from studying in her own city because of who her father had been. She had to leave, study elsewhere, fight her way into the mathematical world through sheer ability and stubbornness. She eventually became one of the leading mathematicians in the Soviet Union, served as president of the St. Petersburg Mathematical Society, and made foundational contributions to the theory of partial differential equations. Her proof that the two-dimensional Navier-Stokes equations are well-behaved is a landmark result. She was, by all accounts, a formidable person, brilliant, tough, and unbroken by circumstances that would have destroyed many. But three dimensions are fundamentally different. In three-dimensional fluid flow, there's a mechanism called vortex stretching that doesn't exist in two dimensions. When fluid rotates, forming a vortex, think of a tornado, or the swirling water going down a drain. The three-dimensional nature of space allows that vortex to be stretched and compressed along its axis, like pulling taffy. This stretching intensifies the rotation, concentrating energy into smaller and smaller regions. This process can cascade. Stretched vortices create more intense vortices, which get stretched further. And the question is whether this cascade can drive velocities to infinity in finite time, whether the equations can literally blow up. It's the mathematical equivalent of asking whether a whirlpool can spin itself into infinite intensity, a question that sounds almost absurd, and yet we genuinely cannot answer it. Nobody knows. And this connects to one of the most fascinating and frustrating phenomena in all of physics: turbulence. You've experienced turbulence every time you've watched smoke rise from a candle. It goes up smoothly for a few inches, and then breaks apart into wild, chaotic curls and eddies. You've experienced it on an airplane when the ride suddenly gets bumpy. You've seen it in a fast-flowing river, where the water breaks into churning white foam over rocks. You've felt it when a gust of wind hits you from an unexpected direction on a windy day, swirling around the corner of a building. Turbulence is everywhere in the natural world. It determines how heat moves through the atmosphere, how blood flows through your arteries, how fuel mixes with air in a jet engine, how pollution disperses in a city, how cream swirls into your coffee when you stir it. The wake behind a ship is turbulent. The flow of gas in a star is turbulent. The air moving around you right now, even in a quiet room, contains tiny, turbulent eddies. And we don't have a rigorous mathematical theory of it. We have approximations. We have computer simulations that eat up enormous amounts of computing power. Simulating turbulence is one of the single biggest consumers of supercomputer time in the world. We have empirical rules of thumb that engineers use every day, but a first principles mathematical theory, one that starts from the Navier-Stokes equations and derives the statistical properties of turbulent flow, that doesn't exist. Richard Feynman, the great physicist, called turbulence the most important unsolved problem in classical physics. Werner Heisenberg, the same Heisenberg who gave us the uncertainty principle, reportedly said that when he met God, he would ask two questions: why relativity and why turbulence? And he fully expected God to have an answer only for the first one. That's a joke, but it captures something real about how deeply baffling turbulence is to the people who study it. Horace Lamb, a British mathematician who spent his career studying fluid dynamics, is said to have remarked near the end of his life that when he died and went to heaven, he would ask about two things: quantum electrodynamics and turbulence. He said he was reasonably optimistic about getting an answer to the first. The Soviet mathematician Andrei Kolmogorov made the most significant theoretical contribution in 1941, proposing that turbulent flows, despite their apparent chaos, have universal statistical properties at intermediate scales, properties that depend only on how fast energy is being dissipated. The idea is that in fully developed turbulence, energy enters the system at large scales, through stirring, or wind, or a fast-moving obstacle, and cascades down to smaller and smaller scales through a chain of ever smaller eddies, until it reaches a scale small enough that viscosity converts the kinetic energy into heat. At the intermediate scales, Kolmogorov argued, the details of how the turbulence was generated don't matter. The statistics become universal. Kolmogorov's theory makes surprisingly good predictions, and it's been enormously influential. But it's built on physical assumptions and dimensional analysis, not rigorous mathematical proof from the equations of motion. Deriving Kolmogorov's predictions from the Navier-Stokes equations remains completely beyond current mathematical methods. So here we are. We have equations that describe fluid motion. Those equations are almost 200 years old. Engineers and physicists use them every single day, and we cannot prove that they always work, that their solutions always exist and remain well-behaved. It's a strange situation. It's like driving a car for 2 centuries without being entirely sure the engine can't just spontaneously vanish. Now, the Navier-Stokes problem sits at the boundary of mathematics and physics, and there's another Millennium Prize problem that sits squarely in the territory of fundamental physics. It's called the Yang-Mills existence and mass gap problem, and it concerns the mathematical foundations of the strong nuclear force, the force that holds quarks together inside protons and neutrons, the force that keeps atomic nuclei from flying apart, the force that, in a very real sense, holds you together right now. Here's what's strange about the strong force. The physical theory, quantum chromodynamics, or QCD, works brilliantly. It makes predictions that match experiments to extraordinary precision. Physicists have been using it successfully for decades, but the mathematical foundations have never been made rigorous. Nobody has proved, starting from the axioms, that the theory is internally consistent, that when you follow the rules carefully, you actually get a well-defined mathematical theory and not a mess of contradictions and infinities. And nobody has proved that the theory predicts what's called a mass gap, a minimum energy threshold that's necessary for the theory to match reality. The mass gap matters because it explains a crucial feature of the strong force. It has a finite range. Unlike gravity or electromagnetism, which reach out across infinite distances, the strong force is effective only at extremely short ranges, roughly the width of a proton. That's why it holds quarks together inside a proton, but doesn't reach across the room. The existence of a mass gap, a minimum quantum of energy for the force-carrying particles, is what makes the force short-ranged. Physicists know this is true from experiments and from approximate calculations, but proving it rigorously from the mathematical structure of the theory is a completely open problem. Making this rigorous would mean proving that the mathematical language physicists use to describe the deepest layer of physical reality actually works the way they assume it does. Let me shift direction one more time, because one of the most dramatic stories in recent mathematical history involves a Millennium Prize problem that was actually solved, the Poincaré conjecture. It was the first, and so far only, Millennium Prize problem to be resolved. And the story of how it was solved is as remarkable as the mathematics itself. Henri Poincaré, the French mathematician who posed the conjecture in 1904, was one of the last great universalists, someone who made foundational contributions across an enormous range of fields. He essentially created the field of topology, which studies the properties of shapes that don't change when you stretch, bend, or deform them without tearing or gluing. He also made major contributions to celestial mechanics, the theory of differential equations, and the philosophy of science. He was so productive that the mathematical community still hasn't fully absorbed all of his ideas. Topology sees the world differently from geometry. In geometry, a circle and an ellipse are different shapes. They have different proportions. In topology, they're the same, because you can smoothly stretch a circle into an ellipse without cutting it. Similarly, a coffee mug and a donut are topologically identical. They both have exactly one hole, and you can imagine smoothly deforming one into the other. The handle of the mug corresponds to the hole of the donut. But a sphere and a donut are topologically different. A sphere has no holes. You can't turn it into a donut without puncturing it. Poincaré's conjecture, stated in 1904, is about three-dimensional manifolds, spaces that locally look like ordinary three-dimensional space, but might have a different global structure, the way the surface of a sphere locally looks flat to a tiny ant, but globally curves around and closes up. The conjecture says, if a compact, three-dimensional manifold has the property that every loop drawn in it can be continuously shrunk to a single point, if you can tighten any rubber band until it contracts to nothing, no matter how you place it, then that manifold must be topologically equivalent to a three-dimensional sphere. In other words, the only compact three-dimensional space with no topological holes is the sphere. For nearly 100 years, the Poincaré conjecture resisted all attempts at proof. There were famous false proofs. At least one acclaimed mathematician announced a proof only to have an error discovered. There were heroic near misses. There were entire research programs that advanced the field tremendously but couldn't clinch the conjecture itself. And then, between November 2002 and July 2003, a Russian mathematician named Grigory Perelman quietly posted 3 papers on Archive, a preprint server where scientists share work before formal publication. Perelman was not unknown. He had been recognized as a prodigy from an early age. Growing up in Leningrad, now St. Petersburg, he had been trained by some of the best mathematicians in Russia, competed on the Soviet Union's International Mathematical Olympiad team as a teenager, scoring a perfect 42 out of 42, and spent time doing research at several American universities. Colleagues remembered him as extraordinarily focused, with an almost preternatural ability to see through to the core of a mathematical problem. He was also distinctly uninterested in the social rituals of academia. He cared about the mathematics. Everything else, the politics, the networking, the self-promotion, he found distasteful. After returning to Russia in the mid-1990s, Perelman had gone largely silent. He was working, it turned out, but working alone, without collaborators, without grants, without any of the usual infrastructure of modern mathematical research. When his papers appeared on Archive, they were dense and difficult. Some crucial steps were sketched rather than proved in full detail. It took the mathematical community several years to fully verify every step of his argument. Multiple teams of mathematicians, in the United States, in China, in Europe, worked through his papers line by line. But when the dust settled, the verdict was clear. Perelman had proved the Poincaré conjecture, and he had actually proved something stronger, the full Thurston geometrization conjecture, which classifies all compact three-dimensional manifolds into 8 standard geometric types. The Poincaré conjecture falls out as a special case. Perelman's method was based on an idea called Ricci flow, developed by the American mathematician Richard Hamilton beginning in the 1980s. The concept is deeply beautiful. Imagine you have a lumpy, irregular three-dimensional shape. You let it evolve over time according to a geometric heat equation, a process that smooths out bumps and irregularities, the way heat spreads through a cold metal bar, evening out temperature differences. Hamilton showed that under certain conditions, this smoothing process would eventually deform any three-dimensional shape into one of the standard geometries. Hamilton himself had tried to use Ricci flow to prove the Poincaré conjecture, but got stuck on a critical obstacle. Singularities could form during the flow, points where the shape pinched off or developed infinite curvature, and those singularities could ruin everything. Perelman's genius was in learning how to handle the singularities. He developed methods to classify them, cut them out with mathematical surgery, cap off the resulting holes, restart the flow, and continue. It required extraordinary technical skill and an almost superhuman ability to hold the global picture in mind while managing intricate local details. Other mathematicians have described his work with something approaching awe, and then Perelman walked away. He was awarded the Fields Medal in 2006, the highest honor in mathematics, often called the Nobel Prize of Math. He declined it. He was awarded the Millennium Prize of $1 million in 2010. He declined that too. By then, he had largely withdrawn from mathematical life, reportedly disillusioned with what he perceived as ethical problems in the profession, disputes over credit, what he saw as a gap between the values mathematics should embody and the way mathematicians actually behaved. He resigned from the Steklov Institute, where he had held a research position. He lives quietly in St. Petersburg with his mother. He doesn't give interviews. He doesn't attend conferences. He doesn't publish papers. When a journalist once asked him through a closed door why he had refused the prize, he reportedly said something along the lines of, "If the proof is correct, no other recognition is needed." So the Poincaré conjecture is resolved. But it was one of 7 millennium problems, and the other 6 remain open. We've discussed the Riemann hypothesis, P versus NP, Navier-Stokes and Yang-Mills. That leaves 2, the Birch and Swinnerton-Dyer conjecture and the Hodge conjecture. These are, honestly, the hardest to convey without getting deep into technical mathematics. But let me give you the flavor, because they're beautiful in their own way. The Birch and Swinnerton-Dyer conjecture is about objects called elliptic curves. Despite the name, these aren't ellipses. They're curves defined by equations, like y squared equals x cubed plus ax plus b. These curves turn out to have an astonishingly rich mathematical structure. They show up everywhere. In number theory, in cryptography, in the proof of Fermat's last theorem. And one of the central questions about them is, for a given elliptic curve, How many points on it have rational coordinates? Coordinates that are both fractions. Some elliptic curves have just a handful of rational points. Others have infinitely many. Brian Birch and Peter Swinnerton Dyer, working in the 1960s with one of the early computers at Cambridge, a machine called EDSAC-2, discovered a remarkable pattern. They computed a certain analytic quantity associated with each elliptic curve, something derived from its L function, and noticed that this quantity seemed to predict whether the curve had finitely many or infinitely many rational points. Their conjecture makes this precise, and it bridges two vast mathematical worlds, analysis and number theory. Partial results exist. Andrew Wiles' proof of Fermat's last theorem relied on deep connections to elliptic curves, and work by Benedict Gross and Don Zagier made progress on special cases. But the full conjecture remains wide open. The Hodge conjecture lives in algebraic geometry, at the intersection of algebra, geometry, and topology. It asks whether certain topological features of complex algebraic varieties, high-dimensional shapes defined by systems of polynomial equations, can always be described in algebraic terms. It was proposed by the Scottish mathematician William Hodge in 1950, and stating it precisely requires years of graduate-level mathematics. It's considered one of the most difficult and most beautiful problems in all of contemporary mathematics. The Hodge conjecture asks, in essence, whether the geometry we can see with algebraic tools accounts for everything, or whether there are topological features that algebra can never capture. The answer would tell us something fundamental about the relationship between shape and equation. Now, we've covered the Millennium Problems, the 7 most famous unsolved problems, each carrying $1 million prize. But mathematics is full of other unsolved problems, some of them simpler to state and, in their own way, even more maddening. And one of them has a reputation for being the simplest-sounding unsolved problem in all of mathematics. It's called the Collatz Conjecture, and here's how it works. Pick any positive whole number, any one you like. If it's even, divide it by 2. If it's odd, multiply it by 3 and add 1. Take the result and do the same thing again. Keep going. The Collatz conjecture says that no matter what number you start with, you will eventually reach the number 1. That's it. That's the whole conjecture. Let me show you how it works with a couple of examples. Start with 6. 6 is even, so divide by 2, 3. 3 is odd, so multiply by 3 and add 1. 10. 10 is even, 5. 5 is odd, 16. 16 is even, 8. 8, 4, 4, 2, 2, 1. Done. 8 steps from 6 down to 1. Now try 7. 7 is odd, so multiply by 3 and add 1. 22. 22 is even, 11. 11 is odd, 34. 17. 52. 26. 13. 40. 20. 10. 5. 16. 8. 4. 2. 1. A longer trip, with some wild bouncing up and down, but it gets there. Now try 27. This one takes a wild ride. It climbs and falls and climbs again, bouncing around dramatically, reaching heights of over 9,000. It hits 9,232, more than 300 times its starting value, before eventually, after 111 steps, working its way back down to 1. Every number that's ever been tested, and computers have checked numbers past 1 billion, up through roughly 10 to the 20th power, eventually reaches 1. No counterexample has ever been found, but no one can prove it. The mathematician Paul Erdős, one of the most prolific problem solvers of the 20th century, a man who published more papers than anyone except Euler, a nomadic genius who traveled from university to university with a battered suitcase, living on the couches and guest rooms of mathematicians around the world, looked at the Collatz Conjecture and said, "Mathematics may not be ready for such problems." And coming from Erdős, who solved problems the way most people eat breakfast, that's a sobering assessment. He also offered $500 for its solution, which was a substantial sum from a man who spent virtually nothing on himself. The conjecture is named after Lothar Collatz, a German mathematician who is believed to have first posed it in the 1930s, though the exact origins are somewhat murky. What makes it so fiendishly difficult is that the operation mixes two completely different kinds of arithmetic. Dividing by 2 is a multiplicative operation. It interacts with a number's prime factorization, stripping out factors of 2. But adding 1 is an additive operation. It completely reshuffles the prime factorization in an unpredictable way. When you alternate between these two kinds of operations, the behavior becomes chaotic. The trajectory of a number under the Collatz process seems almost random, and indeed, probabilistic arguments suggest that numbers should tend to decrease on average, making it plausible that everything drifts down to 1. But turning that heuristic argument into a rigorous proof has defeated everyone. The best recent progress came from Terence Tao, widely regarded as one of the greatest living mathematicians. In 2019, Tao proved that almost all numbers, in a precise statistical sense, eventually reach values that are close to 1. Specifically, he showed that for almost every starting number, the Collatz sequence eventually drops below any fixed bound. That's a big step. But almost all in mathematics doesn't mean all. And the full conjecture, that every single number reaches 1, remains untouched. And the Collatz conjecture is far from the only simple unsolved problem. Mathematics is full of them, lurking in the shadows of the integers, simple to state and apparently bottomless. Are there infinitely many perfect numbers? A perfect number is one that equals the sum of all its divisors less than itself. 6 is perfect. Its divisors are 1, 2, and 3, and 1 plus 2 plus 3 equals 6. 28 is perfect. 1 plus 2 plus 4 plus 7 plus 14 equals 28. The next two are 496 and 8,128. They get rare quickly. Euler proved that every even perfect number is associated with a Mersenne prime, a prime number of the form 2 to the power p minus 1, where p itself is prime. This connects perfect numbers to an ongoing search for ever larger Mersenne primes, a search that continues today through a massive distributed computing project called the Great Internet Mersenne Prime Search, or GIMPS. As of the most recent discoveries, only 51 Mersenne primes are known, but nobody knows whether there are infinitely many, even perfect numbers, and nobody knows whether any odd perfect numbers exist at all. If an odd perfect number exists, it would have to be astoundingly large. Current bounds show it would need to have at least 2,300 digits, but nobody has proved that one can't exist. That question has been open for over 2,000 years, since at least the time of the ancient Greeks. What about the digits of pi? We know pi is irrational. Its decimal expansion goes on forever without repeating. We know it's transcendental. It's not the solution to any polynomial equation with integer coefficients. Trillions of digits of pi have been computed. But is pi normal? Does every digit from 0 to 9 appear exactly 1/10 of the time in the long run? Every pair of digits, like 37 or 05, 1/100th of the time? Every sequence of 10 digits with equal frequency? We strongly believe so. Massive computations of pi's digits, trillions of them, show no deviation from this pattern. The digits look random, even though pi is a perfectly definite, deterministic number. But a proof? Nowhere close. We can't even prove that the digit 7 appears infinitely often in the decimal expansion of pi. Think about that. One of the most fundamental and familiar numbers in all of mathematics, known to every schoolchild, and we can't prove basic facts about its digits. It's humbling. There's a deep philosophical question lurking behind all of this, one that connects back to what Gödel showed us. Are some of these problems undecidable? Could it be that the Goldbach conjecture, say, is true but unprovable from the standard axioms of mathematics? This isn't idle speculation. In 1977, Jeff Paris and Leo Harrington showed that there are statements about the natural numbers that are true but unprovable from the Peano axioms, the standard axioms of arithmetic. Harvey Friedman has constructed concrete combinatorial statements that are true but unprovable from the standard axioms of set theory. The possibility that major conjectures might be independent of our axioms is real. And the most famous example of an undecidable mathematical statement brings us to the strangest territory of all tonight. It's about infinity. Not infinity as a vague poetic concept meaning very big, but infinity as a precise mathematical object with its own internal structure and its own surprises. The story belongs to Georg Cantor, a German mathematician born in St. Petersburg in 1845 and raised in Germany, who single-handedly invented the mathematical theory of infinite sets. Cantor's father was a prosperous merchant who encouraged his son's mathematical talent. Cantor studied at the University of Berlin, earned his doctorate, and took a position at the University of Halle, which was not considered a top-tier institution. He wanted a position at Berlin, the most prestigious mathematics department in Germany, but he was blocked, largely by Leopold Kronecker, an influential mathematician who despised Cantor's work on infinity. And the work was indeed controversial. What Cantor was doing, treating infinite sets as completed mathematical objects, comparing their sizes, performing arithmetic with them, struck many mathematicians of his day as philosophically repugnant, even dangerous. Kronecker called Cantor a corrupter of youth. Henri Poincaré called set theory a disease from which mathematics would eventually recover. Cantor received hostile reviews of his papers. He was denied the academic recognition and positions he deserved. And all of this took a terrible toll. Cantor suffered from severe depression. The first documented episode came in 1884, when he was 39, and spent the last 2 decades of his life cycling in and out of sanatoriums. He died in 1918 in a sanatorium in Halle, malnourished and largely forgotten by the mathematical world. It was one of the great injustices in the history of science. But Cantor was right, and his most startling discovery was this: not all infinities are the same size. There are different sizes of infinity, and some are bigger than others. Consider the natural numbers: 1, 2, 3, 4, and so on. There are infinitely many of them. Now consider the real numbers. All the numbers on the number line, including irrational numbers like pi and the square root of 2, and all the fractions, and all the terminating and non-terminating decimals. There are infinitely many of those too. But Cantor proved that the infinity of the real numbers is strictly larger than the infinity of the natural numbers. There are, in a precise mathematical sense, more real numbers than natural numbers, even though both sets are infinite. He proved this with a beautiful argument called the diagonal argument, and it's worth walking through slowly because it's one of the cleverest ideas in all of mathematics. Suppose someone claims to have made a complete list of all the real numbers between 0 and 1, a list that pairs every natural number with a real number, first number on the list, second number, third number, and so on, going forever, with every real number between 0 and 1 appearing somewhere on the list. Cantor showed you can always construct a new real number that isn't on the list. Here's how. Look at the first number on the list and note its first decimal digit. Choose a different digit for the first decimal digit of your new number. Now look at the second number on the list and note its second decimal digit. Choose a different digit for the second decimal digit of your new number. Look at the third number and its third digit. Choose a different one. Keep going. Down the diagonal. The resulting number differs from the first number on the list in its first decimal place, from the second number in its second decimal place, from the third number in its third decimal place, and so on, for every number on the list. So it can't be any of them. It's not on the list. And since this argument works for any proposed complete list, no such list can exist. The real numbers can't be put into a one-to-one correspondence with the natural numbers. They're uncountable. There really are more of them. Infinity comes in sizes, so the natural numbers represent one size of infinity. Cantor designated it Aleph Null, or Aleph Naught, using the first letter of the Hebrew alphabet. The real numbers represent a larger infinity, the continuum, with a cardinality Cantor called C. And here's the question that drove Cantor to the edge of his sanity. Is there an infinity between these two? Is there a set that's bigger than the natural numbers, but smaller than the real numbers? Cantor believed the answer was no. He believed the continuum, the cardinality of the real numbers, is the next infinity after Aleph Null, with nothing in between. This belief is the continuum hypothesis, and he spent years, agonizing years, trying to prove it. He would work furiously, believe he had a proof, then discover an error. The cycles of elation and despair, compounded by the hostility of colleagues and his own depression, consumed him. He never found a proof. And then, in the 20th century, something happened that nobody expected. Kurt Gödel, the same Gödel who proved the incompleteness theorems, showed, in 1940, that the continuum hypothesis is consistent with the standard axioms of set theory. You can add it to the axioms without producing a contradiction. Then, in 1963, a young American mathematician named Paul Cohen, working at Stanford, just 30 years old, used a revolutionary new technique he invented, called forcing to show the opposite direction. The negation of the continuum hypothesis is also consistent with the standard axioms. You can deny the continuum hypothesis without producing a contradiction either. Think about what that means. The question, is there an infinity between the natural numbers and the real numbers, has no answer within the standard rules of mathematics. The continuum hypothesis is independent. It is neither provable nor disprovable. It's not true and it's not false. Or rather, the standard framework doesn't have enough information to decide. You can build a perfectly consistent mathematical universe in which it's true, and a perfectly consistent mathematical universe in which it's false, and the standard axioms can't tell you which one we're in. It's as if the rules of chess couldn't determine whether a certain position is a win or a draw. You'd need additional rules to decide. Cohen won the Fields Medal for this work, the only time the medal has been awarded for a result in set theory, and the result remains one of the most profound in the foundations of mathematics. And it raises a philosophical question that still divides mathematicians today. What does it mean for a mathematical statement to have no answer? Is the continuum hypothesis genuinely neither true nor false? Or does it have a definite truth value that our axioms are simply too weak to detect, the way a telescope with too little magnification can't resolve a distant star into a binary pair? Some mathematicians, like W. Hugh Wooden at Harvard, believe that set theory should be extended with new, well-motivated axioms that would settle the continuum hypothesis one way or another. Others believe the independence is the final answer, that at this level of abstraction, mathematical truth is not as absolute as we might have wished. The debate continues, and it may never be resolved. And here's the thing about all of these problems: the millennium problems, the ancient conjectures, the foundational questions about infinity and proof. They're not just puzzles. They're not just intellectual challenges for clever people to sharpen their minds on. They're windows. Each unsolved problem is a window into a part of mathematical reality that we can see but can't yet reach. We can peer through the glass. We can see that something is there. We can sense its shape, feel its presence, sometimes even make confident guesses about what we'd find if we could get through. But the window won't open. Not yet. Not with the tools we have. And different problems give us windows into different parts of the landscape. The Riemann hypothesis gives us a window into the deep structure of the prime numbers, the way they're woven into the fabric of arithmetic, controlled by the zeros of a function that bridges number theory and analysis and, apparently, quantum physics. P versus NP gives us a window into the nature of computation and creativity, the question of whether the universe distinguishes between the difficulty of finding and the difficulty of checking, between composing a symphony and recognizing that a symphony is beautiful. The Navier-Stokes problem gives us a window into the physics of the everyday world, the turbulent flow of air and water that we see and feel every day but can't describe with full mathematical rigor. And the continuum hypothesis gives us a window into the foundations of mathematics itself, a place where the very axioms we use to reason about the mathematical world run out of things to say. What links all of them is a sense of humility. Mathematics is often presented as the most certain of all human activities, the one place where we can achieve absolute, permanent knowledge. And that's partly true, but the unsolved problems remind us that certainty has limits, that there is always more beyond what we currently know, that the universe of mathematical truth is larger, vastly, immeasurably larger, than any human mind or any human system of axioms can encompass. There's a quiet grandeur in that. The mathematician Alexander Grothendieck, one of the most original thinkers of the 20th century, once compared mathematical research to the rising of the sea. "You don't crack open a problem the way you crack open a nut with a hammer," he said. "Instead, you immerse the problem in a rising sea of theory, and eventually, the nut opens by itself, effortlessly, because the water has surrounded it, penetrated it, dissolved the barriers. The great unsolved problems are, in some sense, waiting for the sea to rise, for the right ideas to develop, for the right connections to form, for the mathematical community to build up enough understanding and technique and insight that the answer simply becomes visible, obvious, inevitable. The way Perelman's proof of the Poincaré conjecture drew on decades of foundational work by Hamilton, Thurston, and others, each contribution raising the water level a little more until the problem was ready to be solved. And so the unsolved problems wait, patient as stone, patient as the primes themselves, which have been doing whatever they do, being prime, being distributed however they're distributed, following whatever hidden laws they follow, since long before humans existed, and will continue doing so long after we're gone. It's worth pausing here, near the end of our journey tonight, to notice something. We started with the idea that mathematics is the domain of certainty, proof, rigor, truths that are true forever once established. And that's real. When Euclid proved that there are infinitely many primes, that proof is as valid tonight as it was 2,300 years ago. It won't be revised by new data. It won't be overturned by a better experiment. It won't be superseded by a newer theory. It's permanent. Mathematical proof is the most durable kind of human knowledge. Everything else, scientific theories, historical interpretations, philosophical frameworks, is subject to revision. But a mathematical proof, once established, is forever. And yet Gödel and Cohen showed that this certainty has limits. There are boundaries, questions that the standard rules of mathematics cannot settle. The fortress of mathematical truth has walls, and beyond those walls lie questions that are not yet answered, and some that may never be answered within any fixed system of axioms. The universe of mathematical truth is larger than any system we can build to explore it. No matter how many axioms we adopt, no matter how powerful our logical framework, there will always be truths beyond its reach. It's a strange kind of infinity, not the infinity of the numbers themselves, but an infinity of the truths about them, and that might be the deepest unsolved problem of all. Not any particular conjecture, but the question of what mathematics is. Is it an invention? A game humans play with symbols and rules, like chess or language? Or is it a discovery, an exploration of a landscape that exists independently of us, a set of truths we uncover, but don't create? When a mathematician proves a theorem, are they building something or finding something? Are the prime numbers out there in some platonic realm, waiting to be discovered, the way a new continent waits across the ocean? Or did we invent them, the way we invented the rules of grammar? This is the oldest question in the philosophy of mathematics, and it doesn't have a settled answer. The Hungarian mathematician Paul Erdős used to talk about a hypothetical book, the book, in which God kept the perfect proof of every theorem. When Erdős saw an especially elegant proof, he would say it was from the book. He was being playful, but the metaphor captures something real about how mathematicians experience their work. The truths feel discovered, not invented. When a mathematician finally cracks a problem, the overwhelming feeling isn't, "I built this," but "I found this," as if the answer was already there, hidden in the structure of things, waiting. The physicist Eugene Wigner wrote a famous essay in 1960 called "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." He marveled at the fact that mathematical structures, invented by pure mathematicians, with no thought of application, repeatedly turn out to describe the physical world with uncanny precision. Riemann's curved geometry, invented decades before Einstein, turned out to be exactly what was needed for general relativity. Group theory, developed by mathematicians studying abstract symmetry, became the language of particle physics. Complex numbers, once dismissed as mere mathematical fictions, became essential to quantum mechanics. It's as if mathematics knows about the universe before we do. Wigner called this unreasonable. It is, and nobody has explained it. If mathematics is just a game we play with symbols, why should the universe care about our game? Why should the abstract patterns we invent in our minds turn out, again and again, to be the actual patterns of physical reality? This is itself an unsolved problem, not a mathematical one, but a philosophical one that sits at the very foundation of the relationship between human thought and the cosmos. But here's what I think is beautiful about all of it. Whether mathematics is invented or discovered, the unsolved problems are real. The Riemann hypothesis is either true or it isn't. There either are infinitely many twin primes or there aren't. The Navier-Stokes equations either always have smooth solutions in 3 dimensions or they don't. The Collatz sequence either reaches 1 from every starting number or it doesn't. These questions have definite answers, at least unless they turn out to be independent of our axioms, like the continuum hypothesis, which is itself a kind of answer, just not the kind we expected. And the fact that they've resisted the efforts of the most brilliant human minds in history doesn't mean they'll stay unsolved forever. The history of mathematics is full of problems that seemed hopeless until someone found the right idea, the right connection, the right new tool that nobody had thought to build before. Fermat's last theorem was unsolved for 358 years before Andrew Wiles proved it in 1995. using mathematics that didn't exist when Fermat first scribbled his famous marginal note in 1637. Fermat had claimed he had a proof, one that was too large to fit in the margin of the book he was reading. He almost certainly didn't. The proof Wiles eventually found required the full machinery of 20th century algebraic geometry and was over 100 pages long. But the problem had waited, patiently, for 3.5 centuries until the right person with the right tools came along. The Poincaré conjecture stood open for nearly 100 years before Perelman cracked it, using a technique, Ricci flow, that hadn't been invented when Poincaré posed his question. These breakthroughs didn't come from grinding harder on old methods. They came from genuinely new ideas, new frameworks, new connections between fields that had seemed unrelated, new ways of seeing. And the problems that remain unsolved are, in a sense, invitations. They're telling us that the story of mathematics isn't over, that there are ideas waiting to be had, tools waiting to be built, connections waiting to be noticed. There's something deeply comforting about that, if you hold it in the right light. The universe of mathematical truth is inexhaustible. There will always be more to discover, more to understand, more to wonder at. No matter how much we learn, the horizon doesn't close. It recedes. The questions keep going, deeper and stranger, and more beautiful, without end. And each question that gets answered opens up 5 more questions behind it. That's not frustrating. That's magnificent. It means the adventure never stops. Think about where we've traveled tonight. We started with the ancient Greeks, and the radical idea that mathematical claims require proof, that it's not enough for something to seem true or to work in practice. You have to show why. We wandered through the mysterious world of prime numbers, their infinite abundance, their stubborn refusal to follow any simple pattern, twin primes hovering close together like old friends, Goldbach's deceptively simple conjecture that every even number is the sum of 2 primes, and the great Riemann hypothesis connecting all of it to the zeros of a function in the complex plane, zeros that somehow speak the same language as quantum physics. We met Euler, the man who went blind and became more productive than ever. We met Riemann, the shy pastor's son, who wrote 8 pages that changed mathematics forever and died at 39. We ventured into the foundations of logic and computation, where Gödel showed us that no system of axioms can capture all of mathematical truth, and Turing showed us that no algorithm can answer all mathematical questions, and where P versus NP asks whether creativity is fundamentally harder than criticism, whether finding is genuinely harder than checking. We explored the mathematics of flowing water, the unsolved puzzle of the Navier-Stokes equations, the wild phenomenon of turbulence that Feynman and Heisenberg found so baffling, the simple fact that we've been using equations for 200 years without being able to prove they always behave. We climbed into the austere heights of topology, where Perelman proved the Poincaré conjecture and then walked away from $1 million and a Fields Medal, because the proof was enough. We played with the deceptively simple Collatz Conjecture, pick a number, do a simple operation, repeat, and found that even Erdős said mathematics might not be ready for it. And we ended at the edge of infinity itself, in Cantor's paradise, where the continuum hypothesis showed us that some mathematical questions may lie forever beyond the reach of our axioms, not because we're not clever enough, but because the questions themselves transcend the rules we play by. Each of these problems represents a place where human understanding reaches its current boundary and simply stops, not because the problems don't matter or because no one has tried, but because they are genuinely hard in a way that probably requires mathematical ideas and tools that don't yet exist. And that's exciting, not discouraging. Every unsolved problem is a A promise that there are still things to discover, still moments ahead, when someone, somewhere, working late at night, will see something no human being has ever seen before, and the boundary of knowledge will shift outward by one more small, precious step. Right now, somewhere in the world, a graduate student is scribbling in a notebook, trying yet another approach to some piece of the Riemann hypothesis. Somewhere, a programmer is running a computation, testing the Collatz conjecture for the next trillion numbers. Somewhere, a professor is staring at a blackboard covered with symbols, searching for a pattern in the topology of a space she's been studying for years. Most of them won't solve the big problem. Almost certainly they won't. But they might notice something, a connection, a symmetry, a small truth, that brings the solution one step closer. That's how mathematics has always advanced. Not usually in great dramatic leaps, though those happen too, but in small, patient, stubborn steps, each one built carefully on all the ones that came before. Someone proves a lemma. Someone else notices a connection to another field. Someone else simplifies a technique. And slowly, slowly, the fog lifts. The landscape comes into view, and what once seemed impossibly distant starts to feel reachable. Mathematics is the most patient human activity. A problem posed 2,000 years ago is still worth working on today. A proof, once established, never expires. A theorem never becomes obsolete. It never needs to be updated for a new version. The primes that Euclid studied are the same primes that a researcher at MIT is studying right now, and they'll be the same primes 1,000 years from now. In a world where everything changes, where technologies rise and fall, where civilizations come and go, where the things we thought we knew get upended and revised, mathematics endures. Its truths, once proved, are permanent, and its unsolved problems are eternally patient, waiting for whoever comes next. So as you settle deeper into the quiet tonight, let that thought sit gently with you. The questions don't need you to answer them. They've been waiting this long. They can wait a little longer. The primes are out there, infinite and inscrutable, scattered among the integers like stars scattered across the night sky, everywhere you look, and yet following some hidden pattern that nobody has quite deciphered. The zeros of the Riemann zeta function are sitting on their critical line, or not, regardless of whether anyone is thinking about them. The Navier-Stokes equations are describing the air moving softly around you right now as you breathe, the tiny eddies and gentle currents in the air flowing past your lips, governed by equations we can write down but can't yet fully understand. And somewhere, in the abstract reaches of topology, shapes are curving in dimensions you can't visualize, and elliptic curves are tracing their elegant paths through fields of rational numbers, and the continuum hypothesis is hovering in its state of permanent undecidability, neither true nor false, both true and false, depending on which mathematical universe you choose to inhabit. And Cantor's infinities are stacked one atop another, an endless tower of sizes of infinity, each one larger than the last, with no final ceiling, with always more room, always more levels, always more to explore. And the numbers themselves, the whole numbers, the primes, the integers you first learned to count when you were very small, sitting on a floor somewhere, pointing at objects, 1, 2, 3, they're still there, still holding their secrets. They were there before anyone counted them. They'll be there after. They don't need us to exist. They just go on, patient and eternal, the simplest things in all of mathematics, and the source of its deepest mysteries. 1, 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31. The primes go on, the questions go on, and tonight, for once, you can let them go on without you. Let the numbers do what they've always done. Let the unsolved stay unsolved for now. Let the infinite be infinite without needing to be grasped. The problems aren't going anywhere. Mathematics will still be here in the morning, patient as ever, beautiful as ever, its deepest mysteries waiting quietly, the way they always have, the way they always will. Close your eyes. Let the numbers fade to a hum in the background, a soft pulse, like a heartbeat, steady and eternal. Sleep well.